Alright, so what we want to prove is that if you take the closure of an open set U, that's the same thing as taking the closure of the open set U intersected with a dense set A. Alright, so let's see here. One direction is completely trivial. Certainly U intersect A closure will be contained in U closure. And that's because, well, certainly U intersect A is going to be contained in U, and then closures obey inclusions. So if A is a subset of B, then A closure is a subset of B closure. And I don't recall if that's something that's mentioned in the textbook, but you can prove it using the fact that the union of a closure is equal to the closure of a union, so long as it's a finite union. Here you just use pairwise unions because you compare U, or if you're looking at, like, say A is a subset of B, then you write B as a union of A with B set minus A. And I actually went over this in the previous exercise, I believe, so you can look there if you need. But anyway, so this inclusion is straightforward, and the tricky part is the other inclusion. So for the other inclusion, let C be a closed set containing U intersect A. I claim that C contains U. Because what will this do? This will mean that if we're taking the intersection of all closed sets which contain U intersect A, then all of these sets contain U. And so if we take the intersection of this, if we take the intersection of these sets, let's see here, any closed set containing U intersect A contains U. So if we take the intersection of all closed sets which contain U, then this is going to contain, or this is the set of all closed sets which contain U will at least contain all closed sets which contain U intersect A. So let's write this out. U closure equals the intersection of all C closed such that U is contained in C. This is a subset of the intersection of all C closed such that U intersect A is contained in C. And this equals U intersect A closure. Okay, and why does this inclusion that I've written here hold? So if we prove that every closed set containing U intersect A also contains U, then this collection here will be a subset of this collection here. And so if we look at the set on, when we take these intersections, if we look at the intersection on the left-hand side, we're taking an intersection of a bunch of sets, which include all of these sets that we've written on the right-hand side, but it could also include more sets. And so that's going to be contained in this intersection of just these sets over here. And so that's why this inclusion holds. Okay. So now what? We must prove that C is contained in U set minus A. Right. Okay, so I claim that C contains U. So since C contains U intersect A, we must prove that C contains U set minus A. Because if C contains both U intersect A and U set minus A, then it contains all of U. Alright, so how are we going to prove this? Let X be any element of U set minus A. I claim that X is a limit point of U intersect A. And of course, this is, I think Folland calls them accumulation points. I like limit points. Okay, so to prove this, note that since U is open, okay, so what we need to do is we need to prove that every open neighborhood of X contains some point not equal to X, which is in U intersect A. So anyways, to start with, U is open, and so here we're really using the fact that U is open. Since U is open, there exists some open set V such that X is in V, which is entirely contained in U. Alright, so now let W be any open neighborhood of X. So what we want to find now is we want to find an element of W which is not X, but which is contained in U intersect A. And if we can do this for this arbitrary open neighborhood W of X, then that will be sufficient to prove that X is a limit point of U intersect A. Alright, so then W intersect V is an open neighborhood of X which is entirely contained in U. And since A is dense, W intersect V intersect A is non-empty. So, in particular, it contains some element. There is some Y which is contained in W intersect V intersect A. Okay, but the other thing that I'm thinking of right now is, how do we know that Y is not equal to X? Because that's important here. Well, we know for sure that there is some Y in W intersect V intersect A. Well, wait, no, we know that X is in U set minus A, and so X is not in A, so X cannot be in this intersection. So Y cannot be equal to X because X is not in A, and Y is in A. So there we go. At first I was thinking like, okay, well, X is just a point, so maybe if you remove that point, you're taking an open set and removing a closed set. That should give you an open set. But that only works in some topologies. I believe T1 topologies. It only works in topologies where point sets, singleton point sets, are closed sets. It's not true in every topology. And this fact is supposed to hold for every topological space. Okay. But now, so what can we do now? So this is actually contained in, well, V is contained in U. So this is contained in W intersect U intersect A. And that's what we wanted. We need to find some element in, for any open neighborhood W, we need to find an element X no, we need to find an element y, which is not x, and which is in both W and U intersect A. This holds for all such W, and so x is a limit point of U intersect A. Alright, and why is this useful? We know that, okay, so we have this set C contained in U. No, we have the set C containing U intersect A, and we want it to contain all of U. So we choose this arbitrary x, which is in U set minus A, and we want to prove that x is in C. Since C is closed and contains U intersect A, C contains all limit points of U intersect A. Because C contains all of its own limit points because it's a closed set, and so in particular it contains all limit points of the subset U intersect A. So C contains all limit points of U intersect A, and in particular, since x is a limit point of U intersect A, x is in C. So, what does this tell us? This tells us that U set minus A is contained in C. So all of U is contained in C. And this is what we wanted to prove, because now we know that U closure is contained in U intersect A closure. And hence, U closure equals U intersect A closure. There we go. And yeah, so an interesting question that I thought of while we were going through this, or while I was thinking through this solution is, why do we need U to be open? And I guess the real reason is you need to ensure, well, we need x to be a limit. If you take any x in U set minus A, you need this x to be a limit point of U intersect A. And so what you really need is you need to have a bunch of points near x, which are in both U and in A. And first of all, if U is not open, then you can't guarantee that there is an element of A which is in U, because that's what you need for denseness, because that's part of the definition of denseness. Every open set contains an element of this dense set, so that's why you need that. In particular, it cannot contain isolated points. As I'm thinking about this, and I think that having U be open is not entirely necessary. Like, I'm trying to think of examples in, like, on the real line, and if you just take, like, closed intervals, then I wonder if this also works for closed intervals. If you take a dense set, and then, the closure of the closed interval will just be the closed interval, and then if you take you take this closed interval and you intersect it with a dense set, then that should also be the closed interval. But this also might have to deal with, like, more of the topological structures that we have on the real line, which aren't necessarily included in other topologies. So I'm not entirely sure. Certainly you can't have any isolated points of A, or of U. If U has any isolated points, that's bad, because you can just choose, well, you need if you have an isolated point, then you can't force every closed set containing U. No, you can't force every closed set containing U intersect A to contain U. Particularly, I think you need this isolated point to not be an A. And then that gives you a counterexample here. But yeah, this is a nice sort of short exercise, and it's interesting. And now we're done.